Okay, so since last time we finished the shear, I'm going to change a bit the order of the notes. We're going to cover first what we were talking about last time a little bit, which is the single and double shear connections. And again, this should not be new, but it's like a quick review. So a single connection is basically what is the simplest way to connect two plates. Let's say we have one plate here. We'll do this one a bit longer, maybe this one here. And then let's say we have another plate here. So what is the easiest way to connect them is you can put a bolt over here. Let's say this will be the top of the bolt. And here you might have a nut, okay? You can put a washer, no washer, whatever you want. And then let's say this will be subjected to a force F over here and F over here. So again, in order to study this, this is the same thing as a beam, okay? So if you look at the bolt, let's say we take the bolt as being a beam. So I mean, I'm going to do two little figures here instead of just one. This is our bolt here. Okay, if I do a quick sketch that way, what will you have? This part will be holding the force F. This will be F. So now imagine that you need to study this and we make a cut. So let's say we make a cut, I mean, anywhere here. Let's say we made the cut here. So you made a cut. You will have the same thing at the top. Here, this would be the cut. So you will still have the amount of force over here, F. And here you will have a shear force. So as for the beam, when you want to find the shear force, what do? You apply summation of forces equal to 0. So this will give you what? Minus F plus V equal to 0. But we can rewrite the force as what? What is the expression for shear? Is force divided by tangential area. Okay, so let's look at this equation. So this equation means what? This will be, if we look at the force over here, we look at this little figure here. Basically, you are right. Maybe this should not be the distributed force. I put it like F here, but really the force F should be acting in the middle, and this should be what? This should be the value of the stress distribution, which is what I was trying to do. So maybe you are right. Maybe I should do here like a little elongation for F. And here the same thing for F. and just say that this is the distribution for tau, okay, the shear stress. So that's good because that's what we need to do next. So in other words, if we know the force, if we write the force in function of the stress, what do you have? The force is going to be equal to the shear times the area. So minus this plus V equals 0. Or this is going to give you that the shear is equal to the shear force divided by the area. So basically, this is the shear stress produced by a single shear connection. So single shear connection. But next, what could be another way to attach, let's say, more than, or to attach two plates, or to attach more than two plates? So what we can have is so one plate on top, let's say another plate at the bottom. This, and let's see, we can do the one like this. And now we can connect the bolt over here. And put the nut over here. So this time, this is going to be a bit different because if we pull here with the force F, in order to be in static equilibrium, these two plates should be F over 2. Okay, so basically I'm going to do the same thing as before. I'm just going to do, but this time I'm going to make the cut. I mean, I'm going to redo this. I'm going to do more figures. So if I do the same thing as before, exactly the same process as before, we should have one figure that will look this way. So maybe now I need to be careful with if I put the force or not. So this one here will be, oops, I need to break this in 3. So be careful here. I know this should be the force. This should be F over 2. What did I do here wrong? Oh, no, sorry. See, this should be here F over 2. And then this one here, I'm going to make it in green because this one disappears. And then here you should have the F. So here we have the choice about where we're going to make the cuts. Okay, so let's do this both ways since we're doing this. Okay, so let's say we make the cut over here in this area over here. Okay, so we made the cut over there. What are you gonna have? You're gonna have here the force. I like to do it distributed, but you know it's just one force. You're gonna have here F over 2, and then you will have here the shear force V. And basically, as before, when you apply the summation of forces equal to 0, you will have minus F over 2 plus V equal to 0. Now, here the shear will be equal to what? What will be the force? Will be F over 2 divided by A. Okay. Same thing over here, tau over 2 divided F over 2 divided by A, and here tau will be F divided by A. So if since we take this cut here, this gives you the tau here is F divided by 2 divided by A. So this will mean we need to be careful here. So, all right. So this would be equal to what? So the force F divided by 2A. Yeah. So F would be equal to what? Will be equal to tau times 2A. Do you see that? Basically what I'm doing is you have this here, tau equal F over 2A. So this will give you that the force is equal to tau times twice the area. So I replace the force by this one. This is negative plus V equal to 0. So this now is going to give you that the shear stress on a double connection will be equal to V over 2A. So this will be the shear for a double shear connection. Okay, now this is just additional. So you see that all the time the procedure we are doing should be the same. Let's say we make a cut, one here and one here. So what would that mean? So let's say we go here, one cut here, one cut here. So this time you will have here the whole force that I did in green. So it will be tau over F divided by A. And here was the force, the equivalent force F. But this time, what would you have? Since we made a cut at the top and the bottom, we make the cut here. And here, you're going to have a V over here and a V over here. So if both of them needs to be equal to V, you can say this will be half V and this will be half V. I mean, there's two ways to do this, okay? This way. And so now you do summation of forces again, equal to 0. So what are you going to get? Minus V over 2 minus V over 2 plus F equal to 0. Where here F would be equal to what? So with tau over here, would be equal to F. And then how many areas are you gonna have? You're gonna have one area at the top over here and another area here at the top. So it would be over 2A. Or you could say this V and V. So at the end we get the same thing. So basically you get minus V plus tau times 2A equal to 0. So you see we get exactly the same equation, or at the end, tau will be equal to V over 2A. Okay, so here and here we get the same thing as expected. Okay, so why is this important? It's because now next we're going to study how to connect beams between each other. So you can select different ways to connect one beam to the other. You can use single shear connection, double shear connection, or different ones. So I'm going to call this connections or connectors. Let's say connections. And the example I'm going to do is, the easiest way to do is probably just to do an example. All right. So let's say we want to connect. So let us consider the below example. So basically here you have one beam that is fixed to the light. So let's say you want to build whatever, a street light. It's not exactly the same case. And so you have two beams. You have this one here, and now you decide that you're going to put another beam like this. Okay? And let's say you have a force over here of 1,000 newtons, and that the distance between the force, the location of the force, and the center of this of the vertical beam is 10 meters. Okay, so here the whole problem is that let us assume that you want to connect this beam to the other one. Your decision is that you're going to take 4 bolts. All right, and you're going to put them symmetrically right at the connection. So we know this. Do we need anything else? All right, and that would be it. So the goal here is to determine the minimum bolt diameter for your connections of 4. Okay, and I'm going to do a little figure here. Remember that if this is your bolt, all right, we know this bolt will be resisting the load tangential to the surface. That's what it will be, shear. Okay, so first assumption we're going to do is that assume that at this connection, this beam over here is going to be cantilever or fixed, like if it was fixed to the wall. So you assume that this one is not moving at all, no? You assume this one is very fixed. So you can say, so first assumption, so let us assume horizontal beam is fixed at bolted connection. So basically that's the bolted connection. So we can simplify the model. So this will be fixed over here. We can take the beam and I can say, I can put the force over here of 1000 newtons, even though you see might be a bit longer, should not have to change at all. Oops, sorry for that. So I plot this to replace this one, and we know that that distance here is still L equals to 10 meters. Okay, so I'm going to start going a bit faster. What would be the way to do this? Would be to find the reactions, and then you can do the shear and bending moment. Okay, but very quick, what do you know? Here, the shear force, if we make a cut, needs to be on the upper direction, no? Okay, so basically we can say here that the shear force will be equal to what? Will be equal to 1000. Okay, if you want me to do a very quick free body diagram, if I do it from this side, you could have what? You could just say that the 1000 here needs to be counter-reacted by a force over here, no? Okay, and you have assumed summation of forces V equal to 1000. Now, and this will be constant at all location. So if you do the shear diagram, maybe let me do it very quick here. The shear diagram along the length will be constant, okay? All right, but now you should be confident with this. Now, the bending moment or the reaction of the force okay, what will you have? The moment will be equal to force times R, no? So it will be force times L, so it will be equal to 1000 times L times 10. So this will give you that M equal to 10,000 Newton meters. If you needed to do the figure, how will it look like? Will be maximum at the root and will be 0 at the point where the force is applied, no? Okay, again, by now you should be really good at this. So basically we know the force, the shear force, and the bending moment. So what is the moment at the area of the connection? Is 10,000, no? Yeah. What is the shear? 1000. So now, if we go to the connection, so let's see, 16. So now, if we look at the connection area, so basically now I'm just looking at this location here. What do we have? So I'm going to make it big. Okay, so let's say you have four bolts, 1, 2. I mean, this should be symmetric. I didn't do a good job, okay? And here, let's say they give us that this, let's make it up. The length of this area here, let's say it would be 0.5 meter. Really, that's not that important, but let's say the distance between the holes over here is 0.2 meters. Guys, I'm going to change the numbers, so I'm going to need you to do calculations, and that the distance between these two here, let's say, will be the same. Will be 0.2 meters. So this is the center over here of the connection. Let's say this will be symmetric. So basically, if we look at these connections here, what do we have? We're going to have a shear force. I'm going to do it here on the side because I don't want to put it, but over all this stuff, you will have, let's say, shear force. Let me do it right in the middle, doesn't matter. Shear force V, that we know is 1,000. But we also know that it should be around all this stuff. So let's see, the moment is going down. Should be B, you should have a moment M, no? Okay. So basically what we know over here is that V total will be equal to V due to the 1,000 Newton force, this one here, plus, let's call it V sub M, where V sub M is shear force induced by bending moment M. Okay, so the way we're going to find V sub M is very simple. Okay, so what is the definition of a moment? It's force times arm, no? Okay, so in this case, we're going to say that the force, this will be equal to V M times the arm D. So what would be D? D will be the distance between the center of rotation of here and, let's say, the center of one of the bolts. So we can say now that from figure, so this is what I'm going to need. I start needing your help. What would be D? So here, remember, if we go from here to here, if we use the Pythagorean theorem, this will be what? 0.1 square plus 0.1 square. And we take the square of both. What do we get? So it will be 1 over 100 plus 1 over 200. So 2, so 1 over 50 square root. So somebody did a calculation that we get 0.14142 meters. So now this is very simple. We can see over here. So recalling the equation, M equal Vm times D. From here, you can find that Vm will be equal to M divided by D. So basically, we know that the moment created over here, we say was equal to 10,000 Newton meters. Divided by the 0.14142. So what do you get for Vm? So this will give you the force, but this will be the total force in this cross section, okay? So if we made the assumption that every single load, so let's say, so we're discussing yesterday, since we are redoing the calculations, let's decide what assumption do we do. Are we assuming that all the bolts are going to carry the same load? Or do we make the assumption that really we want everything to be carried by 2 bolts? I mean, you see, because we say that if you don't want this to rotate, you always need to have 2 bolts, no? To reduce the rotation. So whatever you want to do, okay? So let's do the first way. They say that every bolt is going to carry the same load. I mean, it would be very strange that two bolts will fail, no? Okay. So let's make the assumption if, go to the next page. If every bolt carries the same load, then what do we have? For 1 bolt, you will have, let's say VB will be equal to VM, the one we calculated, divided by 4. So what would you get if you do the 7.07106 10 to the 4 divided by 4? What do you get?
1.767 times 10 to the 4.
So 1.7. So 17,000. 637. 677. So this is 77. Point something or point nothing?
0.7.
Okay, 0.7 newtons. So this will be the load per bolt. Okay, due to the moment. So remember what we said at the beginning is that the total shear force, okay, carried by the bolt would be equal to the V, which is the 1,000, plus the Vm, which is the induced by the bolt, no? Okay, so here we'll have, so really this should be, so at the end, so let's say the total shear force that 1 bolt carries is what? So V total is equal to the V plus the V bolt over here which is equal to the 1,000 plus the 17,677.7, which is going to give us a V total of 18,677.7 newtons. Oh, here I did a little mistake, or maybe bad assumption. What did we say? Is that every single ball was going to carry the same load, no? So maybe what should I do over here? I should divide the 1,000 by 4, no? To follow the assumption. So you see. So then I'm going to get a different value here. What do you get then for V total? So 17, so 17,900 something.
17927.
17927.7, I'm guessing, newtons. So you see, your result will depend on your assumptions, no? Okay, so finally, now we're going to look at the bolt. So what do we know? We have here the bolt. This is our bolt. We know this would be V total. And if I do here another figure, this will be the area of the bolt, which would be equal to what? Is pi r squared, but this is the same thing as pi diameter divided by 4, no? Okay. So we know that this is a single shear connection. If we do this way, this was a single shear connection. So let's say for single shear connection, we know this would be equal to V over A. So this will be equal to V total divided by pi over 4 d squared. Or if we solve for D, what do we have? So let's say we have 4V total. I'm moving the D over there, divided by pi times tau, and I take the square root. Okay, let me add one thing. Now we know that for the bolt, so this is not the beam anymore. Now for the bolt, we know that the maximum shear that the bolt can take is 15,000 kilonewtons per meter square. So that's a lot. So now let's do it over here. So we do the numerical application. This will give a D equal to 4 times the total was 17,927.7 divided by pi. And this one will be, so 15,000, 10 to the 3. And we take the square root. So hopefully it will not be too small. So this will give you a diameter of what? How much?
39 millimeters.
So it would be 0.0039? 0.039 meters. Okay, so let's say to be safe, what would you take? You could say that this should be, let's say, 40 millimeters of, you could say that you want your diameter to be 40 millimeters, no? Okay, now, what is the reality? Is that you don't go to the hardware store and say, I want a bolt which is whatever, 39 millimeters or 40 millimeters, no? You take whatever is available. And obviously when you will go, you will try to take whatever is available higher than this one, no? If you don't get the same value, a little bit higher, no? Okay, but again, you can see that all this will depend on your assumption. If we take the assumption that you just want 2 of these bolts, let's say they all fail and you want 2 to carry everything, then what should happen? Probably the diameter, I mean, definitely the diameter should be larger, no? But then maybe you need to be careful because then maybe they would not fit over here. Then you need to go back and make sure that they're going to fit over here, no? And there's enough clearance between the holes, but we're not going to get into other stuff, no? Okay, but there's many things to think about. All right. Okay, so we're going to look at what is generally called composite beams. And this should be page 62. Okay, so what is a composite beam? It's very simple. Composite means made out of more than one material. Okay, so I'm just going to do a figure, okay, to show what can happen when you have a composite beam. So let's say you have, this is the cross section of a beam. For simplicity, I'm just taking a rectangular cross section. Let's say 1, 2, 3. So let's say this part over here is made out of one material. So this is 2, and this is made out of material 1. So whatever, imagine this is wood, this is steel. Where would be located the neutral axis? Neutral axis would be located at the, where? What is the definition of the neutral axis? Correct, is where the stresses are 0, no? Okay, doesn't mean that it needs to be right at the CG. Okay, so if that is the case, so all this line here will be the neutral axis. So we needed to plot the stresses. maybe what you will have. So if I do here a line, so what will happen? We know it needs to be 0. So let's say they start from here. So here will be 0 because we know the definition is stresses equal to 0 at the neutral axis. Now, let's say this material here is, let's say this one is softer than the top one, okay? All right. So what will happen? Will the stress be higher or lower on that structure? This one is softer. Should be higher, no? So that you will have a jump over here of the stress, and then this will continue to be 0 at the end. But in this area here, you will have a jump. And this is assuming, let's say, that E2 is lower than E1. So it's softer material. Okay, so what is the procedure to solve these problems? So there is another procedure, but I'm just going to give you the steps. It would be easier. So procedure. There's 2 ways to do this. I'll give you the easy one, okay? Even though I've done it in both ways. So the easy procedure, what do you think it is? What did we learn how to do so far? We know how to do the shear, the other moments, all the other stresses for a structure made out of one material, no? So what could we do? What about that we transform this one into just one material cross section? Okay. So let's say transform cross section into one material only. So then once it's made out of one material, we know how to solve it, no? So what would be the way to solve it? So now this will be the standard procedure. Standard steps, which would be what? Find neutral axis by finding CG. Okay, I'm going to put 3 because otherwise it's going to become 2A, 2B. Now we find stresses for one material cross section, and 4 will be we transform or find stresses for 2 materials cross section. All right, so let's do a problem. And I'm planning to finish it. So there we go. Okay, so imagine that we have a composite beam. Over here. This is 2, this is 1. I still don't know which one is which. So okay, so we know that E1 is wood, and that one has a Young's modulus of 12 gigapascals. E2 is steel, and that one obviously had a much larger modulus of elasticity, and that is 200. Okay, so let's say this will be the example. All right, we know that the width of the cross section is 150 millimeters. The height of the wood is 150 millimeters, and that the height of the steel is 20 millimeters. Okay, and is given to you this cross section is subjected to a bending moment of 2 kilonewtons meter. So this is the bending moment. So this is steel. This is wood. Okay, so here, what we need to do, what is the first step? Transform cross section into one material. Step 1. So here we need to make a choice. Doesn't matter which one we do. You can either make everything out of steel, or you can make everything out of wood. Okay, so let's say we're going to transform everything into steel. Okay, so transform into steel, but it should not matter. You can choose. So if we choose this, then what we need to find out is how much weaker is the wood compared to the steel. So we have E wood over E steel. This will give us what? 12 divided by 200 should be what? Should be 6 divided by 100, no? So it should be 0.06. So N over here becomes our scaling factor. So meaning that our new cross section, if I do a quick plot over here, 1, 2, 3, 4, 1, 2, 3, 4. So this is our original cross section. Okay, we transform over here. So we keep still. So the area of the steel, that one would be unchanged. Which we know this will be the 150. This will be the 20. But now, what would happen to the wood? So obviously, if it's weaker, to represent the wood as steel, it should take a much less surface, no? Okay, so what we're going to do is that in order to keep the same height, what we're going to do is we're going to multiply the 150 over here, the width of the wood, by the scaling factors. So what is that? We're going to have 150 times 0.09, so 6 times 15 is 90. So that should be 9 millimeters. So what we're going to do here now is that this is going to become now. So now this will be here, the wood over here, that becomes, so this is still, that distance here is still 150. But now this is 9 millimeters, which is equal to the width over here, the 150, times the scaling factor, which is 0.06. Okay? So that's it. Really, that's the problem. Because now we can just solve this problem as we know. Yeah? Now we had a composite cross section, which was rectangular, but now once we do the transformation, we have a T cross section. So let's go to the procedure. Step 2 is to find the neutral axis location by finding the CG. So here we go. Maybe let's do it here. So step 2, find neutral axis. So let's say this will be the Y. So if I say this will be the Y location, this is Y, whatever. We're gonna find that the CG, let's call it Y ziggly. And let's start, sorry for that. Maybe I should have done the Y a little bit better here. Be careful here because we're gonna do the Y. We need to select the location. So let's do our origin to do it from the bottom. So this will be our Y, okay? The bottom here is fixed at the bottom. That way we can calculate it. Okay, so we start from the bottom. I hope you remember how to do this. We find this one here. So this will be equal to the of each one of the cross sections divided by the total area. Okay. So we start from the bottom. Where would be located the CG of the steel? It would be located at 10 millimeters, no? In height. Now, what is the area? 150 times 20. So this is for 2. Okay, for the steel. Now we move to the top one. what is it going to be? It's going to be, what will be the distance? Will be, if this is 150, should be 75 plus 20, which would be 95. Times the area will be 9 times 150. So this is now for 1. If we divide by the total area, which is 150 times 20 plus 9 times 150, you should find that the y is located at, do the calculation for me, please. But if I'm correct, 36.38. millimeters, which is 0.03638 meters. Okay, so we need to find the neutral axis. So again, let's redo a figure. So if I redo a quick figure, so now everything is made out of steel. I'm gonna do it a bit bigger. Okay, so let's say we know this is 20 and this is 0.36. So let's say our neutral axis, let's say, will be here. And this will be dy ziggly over here. This is 20, this is 150, this is 9. And all that distance here was also, this is, how much was that? How much was the distance? 150 as well. And this is 9. Okay. So again, I'm going to go a little bit faster by now. So the I, so which will be about this axis here. Okay. That would be equal to what? So we need to use the parallel axis theorem. So let's start by this cross section here that we call 2. So this cross section here, the bottom one. Let's look at this one here. Okay, so this one here. First. What would that be? It would be 1/12 of the base, which is 150 times the height, which is 20 cubed. So we're doing this one first. Now what do we need to do? What do we need to do? We need to move it to the neutral axis. So what is the area? Is 150 times 20. So remember the parallax theorem is I equal to I prime plus A d squared, no? So this is A, and now what will be the distance? Will be the y jiggly minus 10 millimeters. I know that square. So we have done the lower part here, okay? I do points to go to the next line. Now, plus, let's do the top one. 1/12. What is the base? 9 millimeters. What is the height? 150. What is the area? 150 times 9. Now, what is the distance? Be careful with this one. What is the distance between the CG of the second part over here, the long vertical, and the neutral axis? So we know that from the bottom, the CG of the long piece is how much? 20 plus 75. So we know this is 95. So then the distance will be, doesn't matter if we do because it's square, so it doesn't matter if it becomes positive or negative. But if you want, it would be 95 minus y ycg squared. And this gives you that I is equal to 9357974 millimeters to the fourth, or I equal 9.357974 10 to the minus 6 meters to the fourth. Okay, I'm going to put it here. You know that 1 meter is 10 to the minus 3, sorry, 1. So 1 millimeter is 10 to the minus 3 meters. So 1 millimeters to the fourth will be 10 to the minus 12 meters to the fourth. No? That's basically what I do. I multiply this one by 10 to the minus 12. Okay? One to the other. Okay, so we're getting there. So now, step 3, we need to find the stresses, which is what we have been doing so far. So stresses, here we're just going to care about the normal stresses because we are just given the bending load. Okay, so let me redo a figure very quick. Let's say we have here the little figure. Everything is made out of one material. We know the location of the neutral axis. Is y bar. Okay, we know the y bar here was equal to what? 36.38 millimeters. So that means that this distance here is 133.62 millimeters. So in our calculations, we need to find the bending stresses at the top and the bottom. So what is the equation for bending stresses? Is sigma equal to my over I. We know that m is 2 kilonewtons per meter. We know the I and the y. We have y of A, y of B. So we have sigma sub A will be equal to what? 2 10 to the 3 times y sub A will be 0.13362 divided by 9.357974 10 to the minus 6. And this is going to give us a stress at point A of 28.56 megapascals. Okay, at this stage, I don't care if it's tension or compression. It's not the goal of this problem. And sigma sub B will be equal to 2 times 10 to the 3 times 0.36. No, 0.03638 divided by 9.357974 10 to the minus 6. And this is going to give us a distribution, a stress of 7.78 megapascals. So we need to be careful here. So now, stress distribution. Only steel. What would it be? Okay, it would be, let's say, something like this. So we found at the top to be 28.56, and at the bottom to be 7.78. So is this the problem we wanted to solve? No. We need, now what do we need to do? We need to go back to the stresses for composite beam. So we have two different materials, not only one. So here, what we need to do first is to remember our coefficient, scaling coefficient, which was E wood divided by E steel was equal to 0.06. So what are we doing here? Now we're going from this structure over here we want to transform it back into this one. So in this case, what happened is that the location of the neutral axis will be the same. All right, but this will be, remember, this will be the steel. Steel. And the rest of this will be the wood. Okay, so we know that the stress should have a jump at this location. Okay, so if the stress at point A on the steel is 28.56 megapascals, once we move it to the wood, would be equal to N times the stress at point A at the steel. And this is going to give us that the value at point A in wood gives a stress of 1.714 megapascals. Okay, so now let's say at point of contact of the two materials, which is at y equals to 20 millimeters. Sorry for that. Okay, so let's say this will be point C of the steel will be equal to my divided by I, which is, I go very quick, 2 10 to the 3 will be, so the distance from the neutral axis will be y zigoli minus 0.02, the 20 millimeters, divided by 9 point, what was it, 357974 10 to the minus 6. This will give you for the steel to be equal to 3.5007 megapascals. The same stress in the wood will be what? N times the stress in the steel, which will be 0.06 times 3.5007, which should give you 0.21 megapascals. Okay, now I'm running 1 minute behind, but I just want to do the figure, and that will be the end. So basically, as we do the figure, so this is our original figure. All right. What did we have originally? So this is 2, and this is 1. So if we do the stress distribution, we keep the neutral axis over here. So we have, so now remember this, now this is the point where they are connected. So we'll go from 1.714 here to, all right, so we're gonna have to jump over here. This is, we have this, we have this. So the value over here, this one is 3.5007, and the value at this point here is the 0.21. So that's why we have the jump. And at the bottom, this one should be the 7.78. Okay, so